Let's see, page 176. All right. So it says use limit laws to evaluate each limit.
Okay.
And we have the limit as x goes to 2 of the square root of x squared minus 6x plus 3, all under the root.
Okay. That's it?
And it's as x goes to -2 on the bottom. Sorry.
-2 or 2 from the left side?
There's
a difference.
Negative.
In other words,
yeah.
This means 2 from the left.
Right. Yeah, it's just
this is going to -2. So what do we have? The first thing you always do on limit problems is just direct substitution.
Okay.
Okay, so that becomes 4 plus 18 plus 3. Unless I've done my math wrong, that goes to 5.
Wow. That's pretty simple.
Well, not really. It's simple for the first 5 minutes. And then the only ones they're going to give you are the ones that are 0 over 0. Because those are the only ones that are hard. In other words, any of the ones where you can directly substitute and come up with a number, those are a piece of cake. You're not going to get those for long, trust me.
Yeah. That's like a special case there.
Well, they're starting you out on the beginner slopes here.
Yeah. These are just review problems for the...
Okay, well, let's go over a few of them until we get to 0. Here, let me talk about this.
Okay.
What's that limit?
That's 0 over 1.
Which is?
0.
Okay. What's this limit?
That's 1 over 0, which is like undefined. But doesn't it go to like infinity?
Well, that's kind of the same thing as infinity. Kind of. Okay? So, whenever you have 0 over any number, and it wouldn't matter whether that was 3 or 1, the limit goes to 0. If you have a number over 0, the limit is undefined. So the only problems are when you have 0 over 0, such as this. What is the limit of that as x goes to 1? Notice when you do direct substitution, it's 0 over 0.
Right.
Which is indeterminable. However, if you do some factoring, the numerator factors into that, and the denominator stays that. Now you can cross that out, and you got that. And now what is the limit as x goes to 1?
2.
Yeah. In other words, 0 over 0 becomes 2 after you apply factoring. And there's 2 or 3 other techniques that you can apply to change 0 over 0. I want to say simplify, but that's not quite the right word. 0 over 0 is considered indeterminable. The problem is that it can be some number, it can be 0, it can be infinity, it can be anything. And you don't know what it is until you do some math on it.
Yeah.
But anything other than 0 over 0 is quite easy. What's the next one you have?
The next one says Use direct substitution to show that each limit leads to the indeterminable form 0 over 0, then evaluate.
Okay.
And let's just pick this one. So it's the limit of t going to 9, and then it's t minus 9 over the square root of t minus 3, and the square root of t is just its own thing, and the minus 3 is separate.
Oh, yeah, sorry.
Yeah, like that.
Well, and you can see that when we directly substitute, we get 0 over 0, right?
Yeah, that's pretty obvious.
Right. And that's the only difficult problems there are with limit problems. There is no other problem that presents any difficulty at all except 0 over 0.
Mm-hmm.
So when we see a function like this, like I said, there's various techniques to reduce this so that it's not 0 after 0 or 0 over 0. When you see a radical sign, think multiply the top and the bottom by the conjugate.
Right.
And the reason is you'll get rid of the radical sign. When you multiply something by the conjugate, the bottom becomes t minus 9.
Okay.
Do this multiplication. When you FOIL those two things, you get t minus 9.
Mm-hmm.
Okay? The top becomes t minus 9 times square root of t plus 3. Right?
Yep.
Now you can cross the t minus 9's out, and I've got square root of t plus 3. Now find the limit of that as t goes to 9.
Oh, that's easy then.
Yeah, in other words, it's no longer 0 over 0. It is some number. It's 6. And that's what happens with all of these limit problems that are 0 over 0, is there really are only like 3 techniques. We talked about one yesterday where you factor something, and today we're talking about multiplying by the conjugate. Those are the 2 primary techniques. Those are the 2 that you're going to use the most often to solve these limit problems that initially start out as 0 over 0.
Right.
Now, just as an aside, you're familiar with difference of perfect squares?
Mm-hmm.
Well, guess what? It doesn't have to be perfect squares. That factors into this. Something they don't tell you in high school.
Oh, really?
Uh-huh. Doesn't matter whether they're perfect squares or not.
Yeah.
It's the square root of t minus the square root of 9 times the square root of t plus the square root of 9.
Yeah.
Now you'll notice that that cancels directly with that, and I'm left with that where when I substitute 9, I get 6 again.
Same answer.
Yeah, and I'm not sure one is easier than the other. This question of multiplying by the conjugate is a fairly frequent answer that you have to use. So I wouldn't even use this other technique that I just mentioned.
Okay.
When you see a radical sign in either the numerator or the denominator,
Mm-hmm.
think multiply top and bottom by the conjugate of whatever term has the radical sign in it. In other words, in this case, the radical sign is in the denominator, so we're going to multiply by the conjugate of the denominator. And remember that anytime you can multiply any fraction by the number 1 without changing it. And that's all I did, was multiply by square root of t plus 3 over square root of t plus 3, which is the number 1.
Got it.
All right, what else you got? Best thing to do is just do as many of these as we can.
Yeah. So this is like a little mix up.
Okay.
Because this is also over. This was a question from a quiz that we had last week, and the same topic is going to be covered on the midterm. So, it says, show that f of x equals 8x to the 7th.
7th?
To the 7th, yep. Minus 9x to the 6th plus x to the 5th minus 24x.
This is going to be an easy problem.
Plus 3. So, yeah, so it's this, and then it says, so show that that function has a 0 on the interval of 0, 1.
Might have to take that back. No, I don't.
Yeah.
I don't have to take that back. There is a theorem. There is a theorem that says
IVT.
that if something goes from negative to positive, then it has a 0 on that interval. If it's continuous and if it's differentiable over the entire interval.
Right.
Well, this function is definitely differentiable. You've learned about derivatives now, and you probably are allowed to use the power rule.
Not allowed to use the
Yeah,
power rule.
well, doesn't matter. We'll still use it. You might not be able to use it on a quiz, but in terms of understanding these problems, you can tell that that is differentiable over that interval.
Yeah.
There is no point between 0 and 1 where that's not differentiable. There's no corners, there's no cusps, there's no things like that. Okay? So, if we evaluate the function at 0 and it ends up below the x-axis, and then we evaluate the function at 1 and it ends up on the other side of the x-axis,
Okay.
it's continuous and differentiable, that means it's got to cross that point. It can't go from negative to positive without crossing the x-axis, not if it's continuous. There are some functions that will do that. The hyperbolic function, that goes from negative to positive without ever crossing the x-axis.
Right.
The thing is that that is not differentiable right there at x equals 0. It's not continuous and it's not differentiable. So that's not an example of this. Okay? So let's figure out what f of 0 is. That's pretty easy.
3.
Now let's figure out what f of 1 is.
You're going to get minus 21.
Hold on. Oh, okay. You've already done it. Minus 1 even. Yeah, minus 21.
Yeah.
So the fact that 1 is positive and 1 is negative, you can't get from 0 to 1 without crossing the x-axis. Now, I don't know that the curve looks like that. It probably doesn't. This is a 7th degree polynomial. So it's probably something that looks like this. Okay? But the fact is, f of 0 has a different sign than f of 1. f of 1 is minus 21. F of 0 is positive 3. You cannot get from positive 3 to minus 21 without going through 0. So this is the mean value theorem. You can't go from A to B without going through all values in between. It's kind of like saying the following. If you're driving a car and you want to go from 10 miles an hour to 80 miles an hour, you can't do it without going through 50 miles an hour. You can't jump from 40 to 60 without going through 50.
Got it.
That's what the mean value theorem says. Is that it's a continuous function. To get from a low number to a high number, you got to go through all numbers in between.
Yeah, that just clicked, and that just made
0 is one of them. 0 is between 3 and minus 21.
Oh, okay. So then it would not have a 0 on the interval if both numbers were positive or both numbers.
Well, you wouldn't know for sure. It could. In other words, it could look like something like the following. What if it looked like this? And you said, those are the 2 points. Well, there's no 0 between those 2 points, but there's a bunch of zeros. There's a 0, there's a 0, there's a 0, and there's a 0. So between these 2 positive points, there are no zeros. Actually, I didn't word this properly. If I look between that point and that point, I can't guarantee that there's a 0. They're both positive. But in this function, it turns out that there are 2 zeros. So just because they would both be positive doesn't mean there is not a 0. But if one is negative and the other is positive, you can't get from a negative to a positive without going through the 0 line.
Got it.
And all values in between. But that is only true if it's continuous and differentiable, that entire interval. And the reason they gave you this problem was because most polynomials are differentiable. Well, I don't know what happened to it, but when you have a typical polynomial, like you just gave me, that 7th degree polynomial,
yep,
that's going to be differentiable through the entire interval. Because now, if I have this function, that's got problems. That's a hyperbola. That's not differentiable.
David?
X equals 0. So all polynomials.
Hello?
Can you hear me okay, Casey? Did we lose
David?
audio? Can you hear me?
I think something happened with the Wi-Fi.
I will call.
Hello?
Casey?
Hey.
Hey, we lost audio somehow through the GoToMeeting.
Yeah.
I think it just came back. I just heard the beep. Say something.
Hello?
No? I have you over the my speakerphone, but that's all. Let me turn the volume up so I can hear you. We can finish the last 10 minutes by phone for the volume, for the audio. It's not that much difference.
Yeah, sometimes the Wi-Fi here just like drops out for a couple minutes.
All right. Well, that's the beauty of this, is that there's alternate ways to get audio.
Exactly.
The audio is usually a little bit better through GoToMeeting, but it's not that bad through
Much.
the phone. I mean, I don't know what it sounds like on your end, but my end is pretty good.
Yeah, no, it's fine.
Okay. What else we got? What can we do in 8 minutes? Unfortunately, I have a 7 o'clock tonight. Another calculus student that I'll have to go to. But what do we got we can do in 8 minutes?
So another question that I had on the quiz was about discontinuity.
Okay.
So I don't know how long this question is going to take, and if you have like any other like ideas about discontinuity, we can just do those too. But it is f of x equals x squared minus 4x plus 3 all over x squared plus x minus 12.
Okay. First rule. Go ahead.
It says find all the discontinuities and determine the type of each discontinuity.
All right. Well, the first thing you notice is that we're looking at two quadratics.
Okay.
The first step almost always is to factor everything.
Okay.
Well, now I hear you through the phone. I'm going to hang the phone up.
Yeah, I'll hang up.
If I don't hang the phone up, it creates feedback. So, can you hear me okay?
Yeah, I hear you go.
Okay. Factor the numerator.
Yep. That is, I factored, when I did the problem on the quiz, I factored the denominator.
Need to factor both. I'll tell you why. One of these factors is going to cancel with the other one. The numerator factors this way.
X minus 3, x minus 1.
And the denominator factors this way.
X plus 4, x minus 3.
Notice that that x minus 3 cancels with that x minus 3.
Oh.
And that creates not a problem, but a situation. In other words, normally your vertical asymptotes are wherever the denominator is 0. So if I looked at this at one glance, I would say, well, that's at minus 4 and 3, correct?
Yeah.
But that's not really the case. Because I can cancel that with that, the only vertical asymptote I have is at minus 4.
Okay.
However, I do have something going on at 3, and that is a hole. Okay? Now, this is going to be hyperbolic in nature.
Okay.
Actually, it's with 1, not, in other words, the horizontal hyperbola. Well, my horizontal asymptote is 1. I misdrew it. Let's call this x-axis at y equal 1. Okay?
Got it.
So here, we'll make that horizontal asymptote. Now, you can see that it's definitely not differentiable at minus 4, right?
Right.
But at 3, we still have a restriction there. There is a hole at 3 that does not disappear just because we canceled these two factors. In other words, the final version of this equation looks like this: x minus 1 divided by x plus 4, right?
Right.
It would appear the only domain restrictions would be minus 4. But
Yeah.
you always have to go back to the original function. You never lose domain restrictions. If your original function has domain restrictions, they stay through the entire thing. And
Got
the
it.
original function cannot be -4 and it cannot be 3. The only difference is the -4 becomes a vertical asymptote and the 3 becomes a whole. In other words, I still cannot have x be equal to -3, even though this is my function. That is still a domain restriction. And it shows up as a whole, not a vertical asymptote. So you have something that would have been a vertical asymptote that gets canceled out. It stays as a domain restriction, but it stays as a whole. So where is this not continuous, to answer the question?
Not continuous at -4 and 3.
Correct, because you have to lift up your pencil to graph it.
Right.
That is the layman's definition of continuity. If you have to pick up your pencil to graph it, it's not continuous. There is a more mathematical definition that you'll get to involving limits, but you haven't gotten to it yet, so I won't introduce it, especially since I have to go in like 2 minutes here. But so this wanted to know what's the domain and where is it continuous? That's it?
It just wanted to know, find the discontinuities and then determine the type.
Oh, right. Okay.
So,
This is an infinite discontinuity
yep.
because it goes to plus infinity on one side, minus infinity on the other.
Yep.
What are your names for your discontinuities? I never remember these because they're not important to me.
They call that one removable.
Okay, that's a removable one. And what are some of your other names? A jump. Yeah,
Jump.
the only 3 I know are infinite, removable, and jump.
Yeah, that's all we know.
Okay, good. Jump looks like this.
Mm-hmm. Exactly.
So that's jump, that's removable, that's infinite.
Yeah. When I did this problem on the quiz, I didn't include x equals 3 as a discontinuity.
Well, I'm not surprised. That's the mistake that everybody would make. Because by the time you get to the end, you're looking at this. And it doesn't look like x equals 3 should be any kind of restriction. But it's because you have to always stay with the domain restrictions of the original function, regardless of whether you factor out a linear factor from the top and the bottom.
Got it. Awesome.
All right, Casey.
Perfect.
I will let you go and talk to you next time.
Thank you. I'll talk to you soon.
All right.